Chapter 7 is going to discuss the different routing protocols. We've not discussed those yet. So, with this chapter, we'll be able to explain the purpose of dynamic routing protocols, the use of these routing protocols versus static routing, how dynamic routing protocols share route information and achieve convergence. That means that they've become one giant network. Compare the different categories of routing protocols. We'll describe the algorithm used by distance vector routing protocols to determine the best path. Identify the types of distance vector routing protocols. We'll configure the RIP routing protocol. We'll configure RIP-NG routing protocol. The difference there is one is for IPv4, the other for IPv6. Describe the algorithm used by link state routing protocols to determine the best path. We'll explain how the link state routing protocol uses information sent in a link state update. You'll be able to understand the advantages and disadvantages of using link state routing protocols. We'll determine the route source, the administrative distance, and the metric for a given route. And also, we'll talk about the concept of a parent-child relationship in a dynamically built routing protocol. And then we'll compare the IPv4 classless route lookup process and the IPv6 lookup process. And then finally, we'll analyze a routing table to determine which route will be used to forward a packet. A little bit about the background of dynamic routing protocols. They have been used in networks since the late 80s, and one of the first routing protocols was Routing Information Protocol, and we refer to that as RIP. There's RIP version 1 that was released in 88, but some of the basic algorithms within the protocol were used on the Advanced Research Projects Agency network, or ARPANET, as early as '69, so it's been around a while. As networks have evolved, they've become more complex. Routing protocols have emerged to handle things better. The RIP routing protocol has been updated to RIP v2. However, the newer version of RIP still does not scale to large network implementations like we have today. RIP works fine if you have a small office, a small network, but it doesn't work well on the larger ones. And to address the needs of larger networks, two advanced routing protocols were developed. We have Open Shortest Path First, or OSPF, and then we have Intermediate System to Intermediate System. Then there's also the Cisco developed. The ones are the Interior Gateway Routing Protocol, or IGRP, and the Enhanced Interior Gateway Routing Protocol, or EIGRP. Which also scales well with larger network implementations. There were the needs to connect different internetworks and provide routing between those, and you have the Border Gateway Protocol, or BGP. It's used between internet service providers, and BGP is also used between ISPs and their larger private clients to exchange routing information. Most of these have been developed, or all of these were developed using IPv4 addressing, with IPv6 emerging and being used now. There's newer versions of the IP routing protocols that have been developed for IPv6. RIP is the simplest of the dynamic routing protocols, and it's used in this section that we're going to go over to provide a basic level of understanding of what routing protocol does and what it is. Just a quick overview of the routing protocol classifications. With IPv4, we have two distance vector routing protocols, and those are RIP v2 and EIGRP. Our link state routing protocols are OSPF version 2 and then ISIS, and then we have exterior gateway protocols, BGP4. With IPv6, we have our distant vectors are RIP-NG and EIGRP for IPv6. The link states are OSPF version 3, and then we have ISIS for IPv6. And finally, for our exterior gateway protocols, we have BGP-MP. Now, basically, what our routing protocols are used for is they're used to exchange of routing information between our routers. In the past, we have keyed in static routing information where we've actually had to manually key in the routing tables and build them that way. With dynamically learned routes, the routers work together to build their routing tables. The purpose of the dynamic routing protocols includes the discovery of remote networks, maintaining up-to-date routing information, choosing the best path to your destination networks, and the ability to find a new best path if the current path is no longer available. And that would happen if your router went down, your lines went down. That way it has a backup, it knows what to do. The main components of your dynamic routing protocols include your data structures, your routing protocol messages, and your algorithms. With the data structure, routing protocols typically use tables or databases for its operations, and this information is kept in RAM. With our routing protocol messages, the routing protocols use various types of messages to discover neighboring routers, and then they exchange routing information and other tasks to learn and maintain accurate information about the network. And then finally, the algorithm is a finite list of steps used to accomplish a task, and routing protocols use algorithms when facilitating routing information, and for best path destination, it determines how far away things are or how close they are. Compared to the static routing that we've done in the past, our dynamic routing protocols, they require less administrative overhead because we're not having to sit there and key in our static routes. The routers themselves are building our tables. However, the expense of using dynamic routing protocols is dedicating part of a router's resources for protocol operations, including CPU time and network link bandwidth. So if you're using more of your router's resources for that, then you're also slowing down your network to some extent, but typically you're not going to notice this. Despite the benefits of dynamic routing, static routing still has its place. There are times when you need a static route and it's more appropriate to have that than with your dynamic routing. The networks with moderate level of complexities have both static and dynamic routing configured in them. So they're not necessarily one or the other. You can use them in conjunction. When you're starting to identify the benefits of the dynamic routing protocol, there's different reasons that you might want to use static routing, and let's look at a few of those before we dive into our dynamic routing. With static routing, there are some primary uses, providing ease of routing table maintenance in small networks that are not expected to grow significantly. So if you're not expecting to expand, routing to and from a stub network, which is a network with only one route, with one default route out, and is not knowledgeable of the remote networks. So this is your stub network that we've talked about before. Accessing a single default route, which is used to represent a path to any network that does not have a more specific match with another route in your routing table. Those would be the instances that you would use your static routing. Some of the disadvantages of using static routing include they're not easy to implement in a large network. Again, they work best in smaller networks. Managing the static configurations can become time consuming. And if a link fails, a static route cannot reroute the traffic. It's only going to attempt to go the route that you've keyed in for it to go. With that said, your dynamic routing protocols help your network administrator manage the time-consuming process of configuring and maintaining those static routes. Let's take an example here. In this instance here, we have a number of routers with a number of switches, and you might be able to maintain this particular scenario on your own, or your network administrator may. But what happens when your company grows and now you have 4 regions and 28 routers and the switches for all of those, and you're trying to maintain those. This is where your dynamic routing is going to come into play. If you're allowing your routers to learn each other, learn the best paths, and learn a backup path, you're not having to maintain and spend as much time on your different routing protocols. We mentioned the advantages and our disadvantages of static routing. Now let's look at the advantages and disadvantages of dynamic routing. Some of the advantages is that it's suitable to all topologies where multiple routers are required. It's generally independent of the network size, so it can work in a small, medium, or large network. It automatically adapts topology to reroute traffic if possible. However, it does have disadvantages. It can be more complex to implement. It's less secure. Additional configuration settings are required to secure it. The route depends on the current topology, and it requires additional CPU, RAM, and link bandwidth. Now, all of our routing protocols are designed to learn about remote networks and to quickly adapt whenever there's a change in the topology, because more than likely, if your business is growing, your topology is going to change. The method that's used by routing protocol to accomplish this depends on the algorithm it uses and the operational characteristics of that protocol, because there are several, as we have mentioned. Basically, the operations of a dynamic routing protocol can be described by the router sends and receives routing messages on its interface. The router shares routing messages and routing information with other routers that are using the same routing protocol, and that's important. They are sharing and they're using the same routing protocol. Routers exchange routing information to learn about remote networks. And when a router detects a topology change, the routing protocol can advertise this change to the other routers so that they're updating their routing tables as well. All of our routing protocols follow the same pattern of operation. When a router powers up, it knows nothing about the network topology, so it's going to have to learn it. It doesn't even know that there are other devices, other endpoints, other end links. It only has the information that's in the configuration file stored in NVRAM. After your router boots successfully, it applies the save configuration, and if the IP addressing is configured correctly, then your router initially discovers its own directly connected networks. Those are the ones who are plugged in directly to it. After that point, then it's going to start learning the routing information from its neighbors. Now that it's learned its neighbors, the routing table is updated with all the directly connected networks and the interfaces those networks reside on. If the routing protocol is configured, the next step is for the router to begin exchanging routing updates to learn about any remote routes. It does this by sending update packets out all of its interfaces that are enabled on the router, and that's important. It's not going to send it out of the interfaces that are not enabled. Once it has done this and the other routers have received the information, they will send information back through those interfaces, and it will basically learn of the other networks. Our next step, after they've learned who they're connected to and who their neighbors are connected to, the routers are going to continue to send out updates. They exchange the next round of periodic updates, and each router again checks the updates for new information. So it's constantly looking to see if that router has, or its neighbor's routers has learned new information, and if it has, then it updates its routing table. Distance vector routing protocol is typically implement a routing loop prevention technique known as split horizon. And what split horizon does is it prevents information from being sent out the same interface from which it was received. So if router 2 does not send an update containing the network out of serial 000 because router 2 learned about that network through that interface. So it only sends information that it doesn't already know out of the interface that it hasn't sent it out of before. After routers within a network have converged, the router can then use the information within the routing table to determine the best path to reach a destination, and different routing protocols have different ways of calculating this best path. So our network has converged, and it has considered converged when all of our routers have a complete and accurate routing table and they know about everybody else on the network. The convergence time is the time it takes the routers to share information, calculate the best path, and update their routing tables. Our network's not completely operable until the network is converged. So most networks require short convergence times. You've noticed this in the lab when you've worked and you've turned on your routers and you've turned on your switches. You do have some time there that it takes them to come up and for them to learn. So that's what it's talking about. It's convergence time. Convergence is both collaborative and independent. The routers share information with each other, but must independently calculate the impacts of the topology change on their own routes. So just because router 1 has come up with a distance to router 3 doesn't necessarily mean that router 3 is going to come up with the same distance. Convergence properties include the speed of propagation of the routing information and the calculations of optimal paths. The speed of propagation refers to the amount of time it takes for your router within the network to forward routing information. Basically, our older protocols such as RIP are slow to converge, whereas modern protocols such as EIGRP and OSPF, they typically converge more quickly than RIP does.